Imagine a place where time almost stops, light bends into circles, and escape is impossible. Now imagine that this perfect prison is not eternal, that it leaks. So slowly you would never notice, yet so relentlessly that, given enough time, the black hole disappears. This is Hawking radiation, one of the strangest predictions in modern physics. It is also a perfect story for Science in Minutes because it connects three big ideas you already met on this channel. Gravity is geometry, time is flexible, and empty space is not really empty. Start with the problem. A black hole is defined by an event horizon, a boundary where the escape speed equals the speed of light. Classically, the horizon is one way. Matter and light can fall in, but nothing can come out. If that were the full story, black holes would only grow. But quantum physics refuses to let space be perfectly quiet. Even in a vacuum, fields still fluctuate. A useful mental picture is that particle-antiparticle pairs constantly pop into existence and annihilate almost immediately. That picture is not the full calculation, but it points you toward the key idea. The vacuum near a horizon does not look like the vacuum far away. Here is the twist Hawking found in 1974. When you combine quantum fields with curved spacetime, the horizon behaves like a warm surface. To a distant observer, a black hole has a temperature, and anything with temperature emits radiation. This is not radiation escaping from inside the horizon. It is created just outside it. From far away, it looks like the black hole is glowing. So why does the black hole lose mass? Because energy has to come from somewhere. In relativity, mass is energy. If the black hole emits a little energy outward, its mass must drop by that same amount. One intuitive way to say it is this. Near the horizon, the pair picture can split. One member escapes to infinity as real radiation. The other falls inward in a way that lowers the black hole's total energy. In many popular explanations, this is described as negative energy relative to infinity. Again, the real math is deeper, but the bookkeeping result is simple. Outgoing radiation carries away energy, and the black hole shrinks. Now comes the part that surprises people. The smaller the black hole, the hotter it is. Big black holes are colder than outer space. Small black holes are hotter and leak faster. That means evaporation is not steady. As the black hole loses mass, it heats up. As it heats up, it radiates more, so evaporation accelerates. For a stellar mass black hole, the temperature is unimaginably tiny, and the lifetime is absurdly long, on the order of 10 to the power of 67 years for something like the Sun's mass. That is many, many orders of magnitude longer than the current age of the universe. So no, the black holes you hear about in galaxies are not going to vanish in any human timescale. In fact, because the cosmic microwave background is about 2.7 Kelvin, many black holes are colder than their environment and would gain energy overall until the universe cools further. A quick intuition for the hotter when smaller rule. Gravity sets a length scale called the Schwarzschild radius. If you squeeze the same mass smaller, curvature near the horizon increases. In Hawking's result, stronger curvature means higher surface gravity at the horizon. Higher surface gravity corresponds to higher temperature. You do not need the exact formula, but the direction matters. Temperature is inversely proportional to mass. Double the mass and the temperature halves. Make the black hole a billion times heavier and its temperature becomes a billion times colder. That is why supermassive black holes are basically ice. And it is why a hypothetical micro-black hole would be a furnace. This is also why the virtual particles escaping story is only a story. If you remove the horizon, the effect goes away. If you keep the horizon, the effect appears even if you never mention pairs. In the real calculation, quantum fields are expanded in different ways for different observers. What looks like vacuum to one observer can look like particles to another. The horizon makes those viewpoints impossible to reconcile globally. The mismatch shows up as radiation at infinity. And what about the end? If a black hole is isolated and small enough, evaporation speeds up. In the final stages, it would radiate extremely strongly. Popular accounts call this a final burst. The exact details depend on particle physics at energies we have never reached, so the last moments are still an open area of theory. But the broad trend, faster and hotter as it shrinks, is robust. There is a practical consequence hiding here. If Hawking radiation exists, black holes place limits on the early universe. Too many small primordial black holes would have evaporated and flooded space with high-energy radiation. Because we do not see that background, we can constrain how many could exist. So even without a direct detection, the idea has teeth. Finally, notice what Hawking radiation did to the word black. A black hole is not a hole you fall into. It is a physical object with measurable properties: mass, spin, charge, temperature, and entropy. It can exchange energy with its surroundings. In a very long-lived universe, it would eventually fade away. That is a wild sentence, and it only becomes possible when you let quantum mechanics touch the edge of space-time itself. If Hawking radiation is so faint, how can it matter? It matters because of what it implies. It says black holes are not just gravity wells. They are thermodynamic objects. They have temperature and entropy. And that creates a pressure point in physics: information. If a black hole evaporates into thermal-looking radiation, where does the information about what fell in go? That question became the black hole information paradox, and it still drives research today. Could we ever see Hawking radiation directly? From a normal astrophysical black hole, almost certainly not with current technology. But there are two routes scientists discuss. Route 1: primordial black holes. If tiny black holes formed in the early universe, the smallest ones could be evaporating today. Some searches look for the final burst of high-energy gamma rays. So far, there is no confirmed detection. Route 2: analog black holes. In labs, you can create horizons in fluids or optical systems where waves cannot escape. These experiments do not prove real black holes evaporate, but they can test Hawking-like behavior in controlled settings. So what should your brain keep? 1. Hawking radiation is a prediction from combining quantum fields with curved spacetime. 2. The radiation is produced outside the horizon, so it does not violate the one-way rule locally. 3. Energy conservation means the black hole must lose mass. 4. The smaller the black hole, the faster it evaporates. One more useful anchor. Hawking radiation is not science fiction stuff streaming out. For large black holes, it would be mostly extremely low-energy photons, far colder than any detector noise. That is why the prediction is famous, even though we have not photographed the glow. And here is the deeper takeaway. Hawking radiation is not just a fun fact. It is a sign that gravity and quantum mechanics are still not fully at peace. A black hole is where the two theories are forced to speak to each other, and they do not agree quietly. If you want, in the next video we can go one step further and unpack the information paradox in plain language. For now, if this clicked, leave a like, subscribe for daily science in minutes, and comment, do you think information can ever be truly destroyed?